Okay, welcome everyone to the final energy symposium of the fall 2017, I guess of 2017. So pleased to have here with us Jessika Trancik from MIT, from the Institute for Data Systems and Society group. So she is an associate professor there. She does a lot of systems integration concepts, a lot of thinking about energy technologies in the economy, so I'm looking greatly forward to her talk. And her research focuses on evaluating costs, environmental impacts, scalability of low-carbon energy technologies for climate change mitigation purposes. She's, aside from being only associated with MIT, she is associated with the Santa Fe Institute that does a lot of interesting complex systems analysis. She's also had appointments in the past at Columbia University, the Earth Systems program there. So it's a pleasure that she came here. I'm glad that she came to give us a talk today, and we'll take it away. Jessika, please take it away. Thank you.
All right, great. Thank you so much. And hi, everybody. Thanks for coming to this talk. So my work focuses on both understanding the drivers of technological improvement in energy and other technologies, and then also feeding that knowledge back into the process of developing technologies so that we can hopefully accelerate the development of technologies toward the goals that we care about. So one of the objectives that we look at here is, in my research and my group, is to develop clean energy to meet climate change mitigation targets. And you may have noticed, just to kind of start with some background, you may have noticed that clean energy technologies have been changing in recent years. So we can see this by just looking at a few pictures. Here we had a solar panel from the 1980s, and this is what solar energy looks like today. This was a nice 1977 Volvo electric vehicle. Can't get those anymore, but you could purchase, well, maybe there's one we could find somewhere, but you could purchase the Tesla Model X, S, or even the X if you could afford it, or a Nissan Leaf or other electric vehicles. So that's what electric vehicles look like today. And these pictures show just a little bit about how these technologies have been changing. In some cases, they've been improving very rapidly. And this is, in large part, this is a major factor in explaining why we went from this situation at the climate negotiations in Copenhagen to this situation in Paris when an international climate agreement was reached in 2015. Of course, it's not the only factor, but we do think, and I believe that this is true, that trends in improving clean energy and specifically the reduction in costs of various clean energy technologies emboldened leaders around the world to join the Paris Agreement and submit their pledges to the Paris Agreement. So those are pledges that different countries intend to meet to reduce their greenhouse gas emissions, and they also signed on to the agreement as a whole where there was a goal stated of limiting global temperature rise, global mean temperature increase to less than 2 degrees Celsius, and even aiming for less than 1.5 degrees Celsius. At the latest climate negotiations this year, which I attended in Bonn in Germany, right before that we had Syria joining the Paris Agreement, and so now all countries have signed on to the Paris Agreement. The U.S. is the only one that is threatening to potentially leave the agreement. But anyway, so it's kind of an interesting change and very important change that occurred over the years and was in part driven by clean energy innovation. But what's interesting, one interesting thing, is that if you look at the models that predicted over the years rates of change, in this case the rates of cumulative installed solar, wind, fossil, nuclear around the globe, you see some interesting things, and you see that in some cases, and actually in quite a few cases, these models haven't done very well. So these are, here I'm showing one of the major energy models and the predictions that were made over time. And these predictions haven't been very accurate. So you can see that by looking at these trends. As we go from blue to red, we're going to more recent predictions, and you can see that over time, these predictions for solar, for example, were ratcheted up over time to match something closer to the reality, which is the data shown here by the black dots. But with each year, the predictions from this model were, and also from the EIA's model, were less aggressive than what was actually achieved by the marketplace. Now, this is just one set of data, and you can see in some areas they do a little bit better. In the case of nuclear, they overpredict what was actually seen in the market in terms of growth. And so why am I showing this? Well, it suggests that we do have some work to do in predicting and being able to better predict technological improvement. And one of the reasons I would argue that we haven't been very good at this is that we, I would argue, have quite limited understanding of what the drivers of technological improvement are. So if you don't know where it's coming from, how do you predict what's going to happen in the future? You could use data-based approaches, and so those can do, there are some approaches that do well, but to make forecasts. But if you want to be able to predict what's going to happen and also use your resources wisely, decide how to invest time and money in the future to drive further innovation, you would really like to know what works and what doesn't work. And one interesting case that I'm going to highlight in just a small story that I'm going to tell you guys is about solar energy. And one question that we might ask about solar energy is, why did costs fall so dramatically? This is a technology whose costs have fallen by roughly 2 orders of magnitude over 40 years, so that you pay 1% of what you paid about 40 years ago for solar electricity after adjusting for inflation. And so it's an example of a very rapid trend in technological innovation. We estimate that costs have fallen at about 10% per year for solar energy, and that is quite a high rate of improvement over time definitely among energy technologies, and it starts to approach some of the rates that are seen in information technologies. Now, the little story I want to tell is that this past summer, I was giving a talk to a group of energy experts from industry and from government, and these are people in very sort of high-level positions within industry and government. And I asked the question. I asked the following question. And by the way, have they read any papers in preparation for this? No. Okay. So I asked the following question. I said, if you had to estimate the policy drivers that were most important for bringing about the cost decline that we saw in solar energy and photovoltaics, what would your estimates be? And I gave them 4 choices. And obviously, it's tricky to know exactly what the answer is. But I'm going to give you guys the same 4 choices and just see a show of hands. And then I'll tell you what they said, and then I'll tell you what our research suggests. So the 4 choices are, and I'm going to give you 2 categories of public policies. One is government funding for research. And here we're looking at the global level. And we're looking at photovoltaic modules. So this doesn't include balance of system costs. So one category of government policy is funding for research. The other category would be a range of instruments that create incentives for market growth. So we know these are really important for growing markets for photovoltaics. And so I gave, and I'll give you guys, 4 different choices that you can vote for. So I'll just read them out, or I'll say them, and then we'll go back and have you vote. So the first choice would be 10% came from government funding for research, 90% from market growth policies. The second choice would be 30% from research and 70% from market growth policies, 50-50 70% from research and 30% from market growth policies, 90% from research funding, and 10% from market growth policies. So now let's go through and you can raise your hands. So how many people vote for 10% from research and 90% from market growth policies? Okay. How many people vote for 30% from research and 70% from market growth policies? Okay. How many people vote for 50% from research and 50% from market growth policies? How many people vote for 70% from research and 30% from market growth policies? Okay. And then how about 90% from research and 10% from market growth policies? Okay, so you see that there's sort of a, not, I would say in this case, not an even distribution, but kind of a pretty fairly somewhat even distribution. There were people voting sort of along the spectrum. In the case of these energy experts this summer, it was really pretty even, and there was a similar kind of spread, sort of distribution across all the different choices as we saw today. So, you know, what this brings up, the reason I'm bringing this up is, you know, here's a case of a technology, an energy technology, a clean energy technology that a lot of people hold up as the gold standard, or kind of a success story in clean energy, where we've seen dramatic rates of cost decline, rapid innovation. But among energy experts in government and in industry, there's not, you know, there's no agreement on where that came from, right? And we see this in other areas as well, in other kinds of questions that I've asked people, you know, in sort of not very scientific surveys like this one, and then, you know, pursuing a little bit more scientific surveys. But in general, you see that for a lot of these basic questions, like the question of what percentage of cars on the road daily could be replaced by a low-cost electric vehicle and still meet daily energy driving needs in the U.S. What percentage? I'm not going to ask you, I'm not going to make you vote there, but again, there we often see this sort of very wide distribution among experts, you know, as well as among the general public and researchers and academics and so forth. But I would argue that these are very basic questions, and if we can't try to or start to answer really important questions like these, like what actually drove solar energy costs decline, then how can we decide how to invest our time and money going forward in order to bring about further innovation, right? And can we do better in the future than a random guess by studying what happened in the past and maybe understanding something about the mechanisms that were at play? And so I'm going to show you an example of that, and then we'll come to the answer to the question that I asked all of you. And I'll show you how I got there. So we're going to start from actually the level of the device itself, the module, the photovoltaics module, and we're going to look at manufacturing processes and then go up to strategies or human activities like research and development, economies of scale that led to those device level changes. And then we'll go up to the level of policies to try to estimate the effect of these different kinds of policies. And of course there are uncertainties, but as you'll see, by looking and really starting at the level of the device, we can get some insight on what the drivers were here, and I think also some insight about how to invest our time and money going forward to develop technologies that solve these big problems like climate change. So here's the cost decline that I mentioned, that roughly 2 orders of magnitude drop in cost, specifically here shown for photovoltaic modules. And in other work that I'm doing right now, I'm looking at other components of a solar system. So if you have questions about that, I can, a solar energy system, I can answer questions about that. Maybe also the solar system, but it's kind of off topic. So, all right, so what drove this cost decline? Well, what we want to do here is to build on and sort of take a different approach to fill what is an important gap in the literature. So what we had to do here was sort of rethink how we're going to answer this question and then develop appropriate models. And the reason is that the two main approaches that we see in the literature, one being correlational analysis or regression-based analysis of technological innovation trends, and static engineering models, neither one gives us exactly what we want, because for the correlational analyses here, you're looking at how, what is the correlation between various variables, and looking at, is there a strong correlation there or not? And then from that, inferring that there may be some sort of relationship, but we're not actually modeling the mechanisms at play. We're not looking at what actually changed about the technology and modeling the mechanisms. So there's definitely a role for correlational analysis and looking at large data sets, and we do some of that in my group as well. But here we want to actually go under the hood of these technologies to see what actually changed. What was it about the device that changed, or the manufacturing process that changed over time? There's another approach in the literature, which I'm calling here static engineering models, where they do go, where people do look under the hood of technology and look at how features of a device combine to give you the total cost of the technology. And then from there, look at different changes that you could make to the different components of the device and what kind of cost you would end up with after making those changes. I call these static because typically what they do is they look at, snapshots in time, but not at where the cost change came from. So you start at time t=0 and you end at time t=1, and you say, okay, I changed all of these different things about the device. I have my starting cost and my ending cost, but how did those changes that you make quantitatively affect the cost decline? Which ones were most important? Which ones drove the cost decline? Which ones are responsible? And so that we can't get that from looking at these static models, although again, this is an important foundation for some of the work that I'm showing here. But what we're going to do here is to look at both detailed mechanistic models, so go under the hood of these technologies, but then also develop dynamic or models of changes over time, right? So they're no longer static, they're dynamic, but they're not focusing on correlational analysis, they're actually mechanistic models. And so that's the approach that I'm going to outline. And this is a three-step process that, as I mentioned, we've applied to photovoltaic modules, as I'm showing you here, and we're also applying this to balance of system costs. For those of you that know what that means, that's basically all of the other costs associated with building a solar energy system. And so we're also looking at nuclear fission and energy storage, and that's it for now, but that's enough to keep us busy. And so there's three steps to the process that I'll talk about. The first is to develop cost equations. So those are similar to those static models that I mentioned, but we're going to formulate them in a little bit of a different way in order to then be able to go to the next step, which is to derive cost change equations that we can then populate with real data. And these cost change equations are describing the low-level, what I'm calling the low-level mechanisms. Those are changes to the device that affected the cost of the device. And then in the third step, we're going to relate those low-level mechanisms to what I'm calling high-level mechanisms. And these are human efforts or strategies that brought about those low-level mechanisms. And then from there, we'll look at the effect of policy. So this is the starting point for developing the cost equations. And I just want to draw your attention to a couple of things here. One is that this is kind of you can think of this as a general way that you can break down any technology in terms of these P variables, which are boundary prices. So that's the price that you pay for inputs to building your technology. And the phi variables, which are usage ratios. That's how much you need of those inputs to give you the output that you want from your technology. So that could be, the price of input and the amount of that input labor, materials, equipment that you need to produce 1 watt of power conversion capacity in your photovoltaic module. So this is a detailed decomposition. In this work that I'm going to be presenting today, we stopped at the module level. And you can imagine that you could decompose the module into, the sort of a very detailed level, and you can go to kind of the very basic building blocks of that photovoltaic module or that technology. But then if we want to populate these equations with data, we have to pay attention to that as well. And so from this detailed picture, what we do is we develop a kind of reduced form or a simplified and more aggregated cost equation where we know that we can obtain the data for the different variables and parameters in that cost equation. And so this is the reduced form cost equation for photovoltaic modules, where we have three main categories of costs: silicon costs, non-silicon area dependent costs, manufacturing scale dependent costs. And here the results I'm showing you are for silicon, crystalline silicon photovoltaic modules, which still dominate the market today. I think it's about 90% market share for crystalline silicon. And then from, our knowledge of the process of technological change in photovoltaic modules, reading the literature, and so forth, and also performing some initial calculations, these are the key low-level mechanisms that we decided to focus on. So together, the idea is that these low-level mechanisms should explain as much of the cost change as possible. So there's a small residual variable, which I'll show you in a minute, and I'll talk about what that might be capturing. But basically, these changes, these mechanisms here, so changes to module efficiency, yield of the manufacturing process, changes to wafer area, the silicon wafer area, silicon usage, silicon price, manufacturing plant size, those were the key what we're calling low-level mechanisms that we identified that affected the PV module cost. And then the next step was really the main methodological advancement, which was to say, okay, we know that we have discrete data. So we have data on each of these variables for, or these different cost components for different years. And we were able to find 3 years of data for each of these cost components here. And so now we need to derive cost change equations that allow us to estimate the contribution from each one of these mechanisms on all of the components of the cost equation. So these are what we're calling cost change equations. And I'm going to show you an example of one. But this turned out to be, this is, as I mentioned, one of the key methodological advances here, because it's sort of non-trivial to develop this methodology and these cost change equations, especially when we're dealing with discrete data. And so what the cost change equations do is, for each one of the low-level mechanisms or explanatory variables, we estimate the effect on all components that show up in the cost equation. So the three main categories, again, are silicon-related costs, non-silicon area dependent costs, and plant size dependent costs, K there. And to show you just one example for the cost change equation due to module efficiency, we can see the result here. And module efficiency is an important one because, as you can imagine, module efficiency, which is the conversion, it's the conversion efficiency that the module is able to achieve in converting energy and sunlight to electricity. Module efficiency affects all of the different cost components in the cost equation. And so this cost change equation captures that. And now I'm going to show you the results that we got when after deriving the cost change equations for each one of the low-level mechanisms. We're going to see how much each one of those low-level mechanisms mattered. And so I'll show this now for 3 periods between 1980 and 2001, 2001 and 2012, and then for the period overall between 1980 and 2012. And note that the time periods are not the same from this column to that column, but these were the years for which we were able to find data to populate our cost equation, which was a lot of work in itself. But we'd like to expand to more years if we can. So you see a couple of things here. One is that conversion efficiency, that is the conversion efficiency of the module, the efficiency with which you're converting energy and sunlight to electricity, was the single largest driver over the period of 1980 to 2012 to the module cost decline. And the other interesting thing that you notice here is that there were a number of low-level mechanisms that were important that all contributed more than 10%. So there's a handful of mechanisms that each contributed more than 10% to the total cost decline in photovoltaic modules that was observed. So that's kind of interesting, and one hypothesis that I'm working with now is that may be one of the reasons why this technology showed relatively steady and sustained cost decline over so many years, because there were many different knobs that you could turn to keep that cost change going. But that's just a hypothesis that we're working on testing, and once we get results from other technologies, we'll be able to do that. Another interesting thing that you see is that plant size, which has an effect on module costs. The effect of that has increased significantly, and that has become the most important driver. That was the most important driver between 2001 and 2012, where it played a much less significant role between 1980 and 2001. So that's interesting to note. And then now let's relate these low-level mechanisms to high-level mechanisms. And here, I'm going to go through these results pretty quickly, but let me just say that, these are some of the, actually, I forgot to mention one thing, which is, I mentioned before that there was a residual term in the model, and so that's P naught. And so you can see that there is a small residual that we're not capturing with the other low-level mechanisms. There's a couple possible explanations for that. One is that it's capturing a mechanism that we just don't know about. But one mechanism that we think could be in there is a mechanism that has to do with the capital expenditures that go into building your plant. And so that could be the reason why, for example, overall the effect was negative, that it actually contributed on its own to an increase in module costs, but that it enabled a cost reduction through the other low-level mechanisms. But it's tricky to say, but that's one possible explanation. But note that residual term is relatively small. Yeah. Yeah.
The one slide before this, the primary equation. Yeah.
Yeah.
So here, can you talk a little bit about where do you get the estimates for prices or costs for each of the components, right? Do you get them from firms, or do you get them from expert interviews, or what's the primary mechanism? Because that may be relevant in understanding the differences. And are these the same sources for each category that you're considering?
Yeah, so we do consider a range of sources, and so there's a few different sources. But where, and I can go back and look at the details, but so one concern could be, well, if you're getting these estimates from different sources, then maybe the different sources have different measurement bias. We know that there's data uncertainty, for example. So we've looked at that through various means to look at different data sources to draw from a consistent source, but also to look across different data sources, because we know that there is data uncertainty, and you see that even if you look at total costs. So that is really important and something that we've looked at. Now, I can't say 100% for sure that we've gotten rid of all possible biases in the data, because the data just isn't substantial enough to, you don't have enough sources to really say that. But it's an important question, so I can discuss that in more detail in a little bit. So now, But like, yeah. So coming back to the low-level to high-level mechanisms, the process here is a little different from identifying and studying the low-level mechanisms. And the reason is the following. In the low-level mechanisms, what we were doing is we were actually measuring, to the extent with the precision possible, given some data uncertainties, we were measuring the effect and estimation uncertainties, model structural uncertainties to some extent, but we're measuring the effect of changes to the device on the cost, on the total cost of the device. So we're measuring the effect of changes to each of these cost variables on the total cost of the photovoltaic module. Now, so the definition of these different low-level mechanisms is just the equations that I showed you before, one example of which I showed you. So the definition is in the equations, but once we start looking at these high-level mechanisms, there is no equation that can tell me what research and development is, or learning by doing, economies of scale, and so forth. But this actually isn't an issue because for the following reason. And so the way we deal with this kind of conceptually is to just make sure that we're defining these high-level mechanisms. So we choose a definition of each of these high-level mechanisms. And that's what's important, right? The word isn't important. It's the meaning that we're going for here. And so it's very important to, you might think I'm kind of belaboring this point, but it's something that comes up in a lot of studies that use quantitative and qualitative data or definitions. And how do you connect the two? Well, one way to do it is just to make sure that whatever you're measuring is clearly defined. And so I'm going to go through what the definitions are now. So for research and development here, we take a pretty expansive definition of research and development to include research, but also development. And so research and development can be very applied, and it can be very basic. So it covers a very wide range of different kinds of activities. Learning by doing, in contrast, we take a fairly narrow definition, and that's because we wanted to be consistent with the original economic literature that proposed the concept of learning by doing, where the definition in those papers was the learning that comes from repeatedly doing something over and over again, and the efficiency with which workers are able to perform that task, the increasing efficiency with which they're able to perform that task, because they've repeatedly done that thing over and over again. So learning by doing does not include anything that involves a non-routine that involves, for example, an experimental manufacturing line in our definition. It's learning that happens on the main manufacturing line for the modules. So that's the definition of learning by doing. And then economies of scale has to do with bulk purchasing effects as well as plant size effects that affect costs going into building the module. And so what we did was to link the low-level mechanisms to high-level mechanisms based on, again, and here we needed to do some in-depth research, but based on an understanding of what activities led to changes to efficiency, to plant size, to wafer area. We then identify the high-level mechanisms that were associated with those changes. And so I'm going to show you some results here. But let me just say that another thing we did was to perform very extensive sensitivity analysis to say, okay, well, how much of the improvement in yield do we give to research and development versus learning by doing? And we varied that assumption very significantly to see what the effects were. And so the conclusions that I'll draw are robust to those sources of uncertainty, which I can say more about later if you're interested. So what we see is that research and development was the single largest driver, the most significant high-level mechanism quantitatively over the period 1980 to 2012. And this includes not just government research, but also research in private companies. Learning by doing also contributed, and economies of scale was significant. And again, in this period, 2012, we saw a hint of this in the plant size low-level mechanism, but economies of scale grew in importance in the period of 2001 to 2012, so that the importance of that high-level mechanism increased as compared to the earlier period. Now, based on these results, as well as based on that sensitivity analysis that I mentioned a minute ago, I'm now going to show you our estimate for the percent contribution of research and development and market creation policies. So get ready. We're going to review that in a minute. But let me just say that, and this is important, I'm not saying that, I believe that neither one, research and development funding and market creation policies, neither one would alone have been a sufficient condition. They were probably both necessary, and their importance and the role they played neither one could, I don't believe, could have substituted for the other. So let me now, at least not entirely. So let me show you now the estimate. So what we estimate is that roughly 70% of the cost decline came from market expansion policies and 30% from government funding for R&D. So that was the second option that I gave you guys, and I think that actually that option, I didn't count, but I think that probably had the most hands raised, so that's good. But there were a lot of hands raised for the other ones as well. And I wouldn't have expected you to know the answer anyway, unless you had read the paper. But the error bar here is due to those alternative methods for allocating low-level mechanisms to high-level mechanisms. So you can see that we've tried to estimate the error here. But this should really be treated as a rough estimate. But nonetheless, it's interesting because this 70%, this 30% contribution from government R&D and 70% contribution from market expansion policies, the way I interpret that result is that both were really important. And this also addresses what has been a very long-standing debate in policy circles about how the government it doesn't fully address, but it starts to address this long-standing debate in policy circles about how the government should be spending its money in stimulating clean energy innovation, with many arguing that we should invest, with some, I should say, arguing that the best approach is to invest in research and development, that government should invest in research and development, that's taxpayers' dollars, until the technologies are good enough to enter the marketplace. But after doing this research, I can say, and really looking under the hood of this technology and some other work that we've done, I can say that at least in a few cases, that we've looked at in detail, those market creation policies were really important. So those were things like feed-in tariffs, renewable portfolio standards, various policy instruments that created an incentive for market growth. What did this do? This led to many private companies entering these markets, competing with one another, driving costs down, innovating, and that was really important. I don't think that could have been, that same effect, that same result could have been achieved with government funding for research and development alone. And this shows some evidence, I would say, to support that. Now, government funding for research and development was really important, I believe, and particularly in the early years to get these markets going. Now, you might ask, because I said at the beginning that this was a global study, so you might ask, well, which countries are responsible for driving markets and for funding R&D? And I'm not going to show you the R&D plots, but I will say that the U.S. has played a very important role in funding solar R&D. And if we look at market expansion policies, we see a couple of interesting things. So here I'm showing cumulative installed photovoltaic capacity in a number of different countries. We know that that was stimulated by various kinds of market expansion policies. And you see a couple of interesting things. One is that, although the efforts rose and fell within individual countries, globally, through a sort of uncoordinated process, what emerged was a rather steady exponential increase over time in the total installed cumulative photovoltaic capacity. So that's kind of interesting. And of course, that's an effect that emerges from these policies as well as the cost decline that we just looked at a minute ago. And you also see that Japan was the leader in the 90s going into the early 2000s, and then Germany took over as the leader in right around 2004. And then in the most recent years, China has emerged as the leader in cumulative installed photovoltaic capacity. So, this is interesting, I think, too, because it really shows, how through this kind of research, we can not only identify some of the determinants of the cost decline, but we can also identify what countries were responsible. And then if you look at per capita investments and so forth, you can say, who around the globe contributed an outsized amount to driving clean energy costs down. And in the case of solar, Germany is very important. In the case of wind, Danes contributed per capita a very large amount. And so that's something that will go down in the history books. They made a very significant contribution, I would say, to not only driving down the cost of this clean energy technology, but also in getting us to a point where the Paris Agreement could be, where we were able to, getting us to a point where something like the Paris Agreement was possible. Now, the Paris Agreement alone is not enough to meet climate targets that have been set, but it does get us some of the way there. And so if we look at what we expect to see under the Paris Agreement, and this is a report that we did to estimate how much growth we might see in solar and wind energy under the Paris Agreement, you can see that we estimate here that solar photovoltaics could grow by a factor of nearly 5 and wind by a factor of nearly 3 under the pledges that countries submitted to the Paris Agreement. And if this investment is used wisely, then this could potentially drive costs down even further and potentially allow for what the signatories to the Paris Agreement intend, which is continually increasing ambition in terms of their emission reduction pledges. So we'll see if this happens, but one of the thoughts that I want to leave you with is that we may be able to do better than a random guess in trying to get this to happen. So one of the things that we can also do with this tool, once we have it, is to perform prospective assessment of different scenarios for reducing costs, both in terms of trying to support those high-level mechanisms that could lead to cost decline, as well as low-level mechanisms. And here I'm just showing 2 scenarios. This isn't this isn't an optimal scenario or anything like that, but it's just indicating that one can also use this as a tool to explore scenarios going forward. But now let me just leave you with the thought here that, or sort of leave you with these results here. Why did photovoltaic module costs fall? Well, we learned that efficiency was really important, yield was important, and a number of other low-level mechanisms were responsible. R&D and economies of scale dominated the high-level mechanisms, and market expansion policies and government funding for research and development both played critical roles in reducing costs. But there's still work to be done to reduce costs further to achieve cost competitiveness. So what I'm showing here are levelized cost of energy estimates for different technologies. You can see that wind looks roughly competitive with natural gas and coal, and solar is sort of starting to get there, and costs have come down since 2015 even further. But this doesn't capture the value of energy. And solar and wind are only available when the wind is blowing, the sun is shining, unless you have storage. And so another important component of reaching cost competitiveness is to develop storage technologies. And I don't have time to talk about it today, but one of the things that we've done in my research is to try to quantify cost targets for storage plus solar and wind in order for these technologies to be truly cost competitive. And this turns out to be a complicated process because, and I won't go into the details here, but you have different parameters, different cost parameters in terms of energy capacity and power capacity for different storage technologies. In order to estimate cost targets, we really have to look at the patterns of energy supply and demand. And only then can we differentiate between different storage technologies which have different features and also set cost targets. Similarly, to estimate the needs for storage and transportation, we have to look at very detailed patterns of which we've done of energy consumption in vehicles. So we looked at this across all cities in the US, and only then can we estimate basically how good batteries are today in terms of their gasoline substitution potential when you consider range constraints of electric vehicles, and then also what the returns might be to improving batteries further in terms of being able to substitute more gasoline. And so I'm going through these results really quickly, but feel free to ask questions about them. By the way, this result here is shown for, now I'm not showing the Tesla, that result is actually shown for the Nissan Leaf, which is a low-cost car, so it's a below-average cost car, and it also saves, it's a much lower emission car than the average car sold in the US today. So, already what we estimate is that 87% of cars on the road daily could be replaced by the Nissan Leaf and still meet daily energy needs of drivers. But again, that's based on looking at the detailed patterns of energy consumption, because in order to estimate vehicular energy consumption, we need second-by-second drive cycle data. And so that's the model that we developed allows us to do that. So finally, I'll just leave you with a couple of key insights. I have presented some research today which I believe shows that we can identify the drivers of clean energy innovation from the level of devices to policies, and that knowledge of past drivers could be used to inform future strategies and hopefully allow us to make wise decisions about how to use scarce resources going forward to develop clean energy and other important technologies. And then if we want to quantify targets that we need to reach for cost or other performance characteristics, we really need to look at the patterns of energy supply and demand when we're dealing with these intermittent resources. And really the whole idea here behind this research is to bring more information and knowledge into the process of developing technology so that we can hopefully do better than a random guess, and we can put our limited time and financial resources to good use to driving down the costs of clean energy and addressing climate change. So I'll stop there, and hopefully we have time for a couple questions.
Thank you. All right, questions, go for it.
Yeah, could you?
Oh, by the way, if you want to check out your car, if you have a car, many students don't have cars, but anyway, you could go to carboncounter.com to see how your car compares to climate targets. Yes.
Yeah. Could you go back to like one of your first charts that showed as a time series with the cost, basically? Right there.
Yeah.
Okay, so if I look at that chart and using your methodology at about 2007, I see something that is radically different from after 2007, before 2007. Let's take your model and use it at, say, 2006 to look forward. What would it see? Would it see that precipitous drop in about 2007 or not? If you're looking at essentially kind of predicting where costs are going to go based on assessment of these different low and high level elements.
Oh, well, so this model, the model that I presented, is about understanding the mechanisms that have that have been important in the past. If we want to make a prediction, there's a couple things that we can do. So one way to make a prediction, which I've also done a lot of work in that area, is to use more of a phenomenological modeling approach and take various proposals that have been put forth for explaining these trends. So one, for example, is what I call Wright's curve or the learning curve. So there, what you would do is you would fit the data to that curve, and then we've also developed a way to forecast the error associated with a future forecast. And so from that, you can build a forecasting model to forecast the cost. But the work that I talked about today is more about understanding mechanistically what caused the costs to come down. So if we...
I would assume then that if you understand that, then you ought to be able to use it.
Yes. So the way that you could do that, so the previous approach I just talked about is basically just taking past data. It's sort of not an engineer's kind of approach, right? It's taking past data and saying, okay, based on what we've seen in the past, what are my forecasts going forward? Right, so it's forecasting based on what we've seen in the past. But an engineer or a policymaker might want to say, well, how can I do better than the past? You know, how can I drive costs down as effectively, as efficiently, or as effectively rather, and efficiently as possible? And so I went over it pretty quickly, but one way in which you could use our model is to, for example, take the cost equations, the cost change equations, and we're also working on developing those to more kind of detailed levels within the device, perform expert elicitation using those so that you actually can ask people about characteristics of the device that they know about and they work on. A lot of expert elicitations haven't been very accurate in the past because we're asking people questions that they can't really answer because it's not what they work on. That's a whole other story. But so you could take that, or you could also, a single lab could use that prospective model to investigate different scenarios. A R&D portfolio manager can use it to investigate different ways to emphasize R&D on experimental manufacturing lines, for example, versus other strategies. So it's a way to, really if you want to make a prediction, past data is really your best friend. If you want to predict what you could do better, how you could, optimally pursue cost reduction in the future, then I think you would want to use, you want to look at past data as well, but then you also want to have this understanding of the mechanisms, and that's where you could use the tool that I mentioned.
Clarification, what happened in 2000?
Oh, yeah, so in 2008, and one of the things you might have been asking is, what if I had stopped in 2008? What would I have seen? Well, what I would have seen is the effect of an increase in PV grade silicon prices. What happened is that the PV industry was growing, but it was still using it was using silicon that was kind of left over from the semiconductor industry, the chip manufacturing industry, that wasn't quite at the level of purity that was needed for chip manufacturing, but was high enough purity for PV. And so they were getting their silicon primarily from there. And but there was growth in the industry, and so that basically, supply and demand, that increased the price of silicon. So if we had stopped our model there, we would have seen that effect. If we had data at the level of detail needed for that year, we would see that effect in our model. What happened after that is that process became vertically integrated, or, so it was taken, PV companies began producing PV grade silicon as an objective, rather than just using what was left over from the semiconductor industry, from the chip manufacturing industry.
Yeah, thanks so much. Excellent presentation. A couple things. It seems like if your equation was mostly focused on, say, manufacturing variable cost, and so it has to have some portion when you talk about kind of scale, because that may incorporate some of the fixed costs. But I just wonder about some of the other factors, how you'd roll them in as far as fixed cost allocations. Just simply the amount sold, helps amortize and reduce the per unit cost of fixed costs. So can you describe more about some of the factors that are fixed cost. And there were many subsidies, how in terms of free land, free infrastructure, subsidized tax base that helped with that. So the fixed cost aspect. And the second question has to do with, that percentage that you saw of market stimulating versus R&D. What are the general trends you see technologically where that ratio should change over time? Seems like some people call that a technology push versus demand pull type of mechanism. And I would think that there might be some general rules of thumb on which way to bias it at what point of technology readiness.
Yeah.
And then over the life cycle, how it should be tuned. If you have any insights on that.
Yeah, so I guess just to start with the second question, then I'll come back to the first one. I can't say for sure, but at least what we see here is that important role of government, what I think we see, and by the way, I should say that one of the things we're doing right now is to develop even lower level mechanisms. So look and actually look at where around the world people did this work. And actually, I'd love to talk to Varun about this because I know he's working on some similar topics, and sort of what labs, and because I think it's going to reveal probably a very interesting collaboration between industry and academia, and a whole set of insights there. But yeah, so. Coming back to the question,
Technology push versus
yeah,
over this life cycle.
yeah. So what we see, so there are hints that and I don't, for various reasons, don't love those terms because I think they're not as informative as they could be. But we see various hints that R&D was quite important, in the early years, and a lot of that was government funded R&D, and actually a lot of it was funded by the U.S. And that, in more recent years, the markets that were, really Germany, Japan as well. Japan played a really important role, and then Germany really kicked in at a very important time in this industry where to grow the industry as they did, they were, as you may know, adopting huge amounts of solar energy, and that really created a market for that was filled by, that was sort of stimulated a lot of activity around the world, including innovation by Chinese firms, and and that brings me to the question of subsidies. Now, there are cases where, some of these cost components may include subsidies. Now, what we know is that those have kind of waxed and waned at different points along this time series. So it is important to, pick, given the limited years that we're able to obtain data for, it's important to choose those carefully. I don't think the primary driver here in those low-level mechanisms is subsidies, but there may be an effect there. But I don't think it certainly doesn't explain the 2 orders of magnitude cost decline that was seen over that time period. That would be a major, a huge subsidy, and that's not, the level that we're seeing. Now, in terms of the fixed costs, yeah, so there's another paper that I'm writing which goes into a bit more detail on the economies of scale effects on PV. And there are a couple of different types of scale economies. So when we look at that economies of scale high-level mechanism, that includes effects of bulk purchasing, that includes effects of higher capacity factors. It includes effects of kind of geometric effects. So the traditional economies of scale example is the surface area to volume ratio. That decreases as you increase the scale of components of a manufacturing plant. So that's in there too. So we're trying to tease out those factors. But again, it's a tricky thing to do, and we're always working with limitations in data and data uncertainty. So I guess, yeah, one thing is if you guys are working in this area, you do really want to pay attention to data uncertainty and draw conclusions that are robust to data uncertainty as well as any structural uncertainty that you may have in your model.
I had a question about, I guess it's like a continuation of his question, was one of the first things in life cycle analysis is you define system boundaries. And here, I think what you had focused on here was just on a plant scale, both for a low level and a high level view of what you were focusing on. But what happens if you include transmission losses, or you include everything, all the losses until the consumer gets it right at the end, the the energy?
Yeah.
And
Right. So so for the low-level mechanisms, you're right that those are at the level of a manufacturing plant, and that should be representative. The goal is to have a representative manufacturing plant there. That's what we're trying to capture with our data, and to the extent that the data has been sampled correctly, there's always sampling issues with this kind of data, but it should capture a representative plant. The high-level mechanism should really capture the, again, a sort of representative picture of the industry as a whole, right? And what occurred and what caused those changes in that representative plant. So we are really aiming for the industry as a whole. What would be the effects of looking further downstream, I think, was one of the things that you asked about. Well, that's where you really want to start looking at the rest of the solar energy system, the installed system. And there's another component of costs that are called balance of system costs, and that includes hardware, and that also includes soft costs, what are called soft costs. Now, hardware costs, the main component is the inverter, and that's something that is bought and sold in a global marketplace. And so some of the trends there are expected to be similar in certain ways to what I've shown here. But for the soft costs, what we know is that they vary a lot from location to location, and some places are much more efficient in installing these systems, and some are less. And we're actually developing a similar model now to look at the soft costs. But there, we really need to look at many different locations. This global analysis doesn't really tell us, as much as we would like to know in that case. And so there are, basically, what the picture that's emerging is that there are certain efficiencies that certain countries and certain, with certain like political systems and systems of regulations are able to take advantage of, and others where others are not. And so there's huge changes and differences in like labor efficiency and factors like that across different locations. So we're trying to, Yeah, so like in Germany, the balance of system costs, I think the latest, last time I looked, they're about half the cost, the balance of system costs, at least the soft cost component, to what we have in the US on average. And yeah, is that what you've seen as well? Yeah. So it's a pretty big difference. And then if you look at India, there you have even lower balance of system costs, and some of that may be lower labor costs, but also I know that there are a number of Indian companies that are really doing some very innovative work in reducing balance of system costs, like through, kind of knowledge-based engineering and approaches that, very kind of strategic approaches. So they're doing some really interesting work in that area.
So my question's about kind of, I guess, a roadmap of how, I guess, your take on market engagement or expansion, how you see it going forward. A lot of what you have shown can be used to kind of, guide the decisions. And him and I work in a company that do demand response, and so we get to see in some instances where there's a mismatch between, the capabilities of new technologies versus in certain markets and areas around the country, how they're being applied and how they've been adopted. And so you're seeing kind of big, trends in wholesale prices and things like that. How do you see, I guess, just maybe your opinion on how some of this data might guide the market expansion going forward, knowing how things have been adopted we'll stick to solar and wind, but I'm just interested to see how you think that this information can guide expansion in industry, across the country.
Yeah, so, I guess I'll say two things. One is that the going forward, we're actually now at sort of a threshold in many places, and in many places we've already crossed that threshold, where solar and wind are having a measurable impact in certain locations on electricity prices, and where, for these, even with subsidies and policies for these technologies to continue to be profitable, to expand, we need to think about how to deal with the intermittency. And so either shifting demand to when there's supply, or shifting supply to when there's demand. You can, through demand side management, shift demand to when there's supply, through energy storage, incorporating energy storage or transmission expansion. You can shift supply to when there's demand. And I think that there is the potential for transmission expansion in a number of places. I think storage is going to be really important. So and it's one of the key remaining technological challenges, and also where there's a lot of opportunity right now in developing new technology. So one of the things that I'm working on is to, as I mentioned very briefly, is to quantify cost targets and compare different storage technologies. The industry has struggled to do that because you can't do it in the absence of looking at demand and supply patterns. But what we've done is to look at demand supply patterns. We've identified some regularities across locations that basically allow us to say, okay, this is the kind of storage technology that could be profitable today. This is where we need to get to in the future. And basically the trade-off between energy capacity and power capacity costs, that optimal trade-off changes as you see more renewables adoptions. We're trying to quantify that. Some of the technologies that look promising are ones where you can really reduce energy capacity costs significantly. So if you're building a flow battery, invest more in power capacity. So your stack, you might have to pay more to build your stack, but really try to reduce the cost of the electrolyte. So we're working with a number of labs to guide some of the work they're doing. But yeah, I mean, you also hinted at, are there steps that one could take just in how we're designing markets and sort of how we're thinking about where to expand. And I think that's also where data and some of these models can really play a role by looking at, okay, well, what is the value of solar or wind in this location? What about if we add storage? What about if we integrate these markets, and sort of predicting that? I think that's definitely something we can do. I don't know if you guys do that, but I see some movement in that direction also in the private sector.
I had a comment about the number. Oh,